HCV is a linear single-stranded RNA virus whose genome encodes a single polyprotein of 3,000 amino acids. The protein is then processed by both host and viral proteases into structural proteins and non-structural proteins that assist in viral replication. Several steps are fundamental for HCV to infect a cell, replicate, and then release to infect other cells. Each of these steps is a potential target to interrupt replication, rendering this virus inactive. The HCV RNA is surrounded by an icosahedral shell of protein, which is then surrounded by a lipid envelope made from modified host cell membrane. Although the exact mechanisms of HCV cell entry are still unknown, it's thought that the envelope proteins on the surface of the virus bind to host CD81 and other cellular molecules, allowing HCV internalization. Once bound, HCV is internalized through endocytosis. The plasma membrane folds inward, bringing HCV into the cell. HCV travels through the cell cytoplasm to the rough endoplasmic reticulum. Ribosomal subunits associated with the RER serve as translation units, converting the message coded in the mRNA to a specific sequence of amino acids, the HCV polyprotein. Translation of the HCV genome results in a large polyprotein that is then cleaved by host and viral proteases to produce 10 viral proteins, 3 structural proteins used to assemble new viral particles, and 6 non-structural proteins which support viral RNA replication. Inhibition of the NS3 protease severely compromises NS protein processing, RNA replication, and viral assembly. The enzyme is a target of a highly anticipated protease inhibitors currently in clinical trials. Although designing an inhibitor was difficult due to the shallow substrate binding groove on NS3, 2 compounds, telaprevir and boceprevir, are now currently available for use. The non-structural proteins NS3 and S5b facilitate HCV RNA replication, first by assembling the membrane-associated replication complex responsible for synthesizing RNA, and then by recruiting the genomic RNA into the complex. Although all the NS proteins are essential for replication, the NS5b protein encodes the RNA-dependent RNA polymerase responsible for RNA synthesis. Although the actual function of NS5a remains vague, it is vital to the replication process, and agents that target this protein inhibit HCV. Since NS5b is responsible for synthesis of both the negative strand RNA intermediate template and the positive strand genomic RNA, it has emerged as a natural therapeutic target. Several HCV polymerase inhibitors are in development. These direct-acting antiviral drugs can be either nucleoside or non-nucleoside inhibitors. Nucleoside inhibitors are analogs of their natural substrates. The polymerase attempts to incorporate the analog into the growing RNA chain, resulting in chain termination and binding of the enzyme's active site. It is thought that resistance will be uncommon with these agents, as they incapacitate the active site. Non-nucleoside inhibitors achieve the same effect by binding directly to the enzyme, causing conformational changes in the polymerase. Drug resistance is more common in NNIs, as they bind areas distant to the active site. Several polymerase inhibitors have been developed and are advancing through the clinical trial process. All of these have demonstrated excellent short-term antiviral activity. The last stages of the viral life cycle are poorly understood. The virus is signaled to switch from replication mode to assembly mode. This may be triggered by phosphorylation of NS5a. Nucleocaspid assembly involves packing genomic RNA in the icosahedral shell of protein, then surrounding the structure with a lipid envelope made from modified host cell membrane.